Swayam Prabha. Digital India. Educated India.
Good morning. Today okay. Today I was looking at the watch to see that I don't go overboard. Yesterday I didn't see what time I start. So, okay. Yesterday we discussed one feature of the world, namely some of the things that we do in science necessarily involve talking about distances and time intervals. And then we motivated that from the practical problem of maps and what you do with that, etc. Use one important information from the property of nature, namely speed of light is constant in vacuum and independent of the source from which it is emitted or the receiver which receives it. That fact led us to a particular kind of map which told us a rule as to how to compute intervals. Now, instead of distances, I am calling intervals because we are talking about intervals between two events which have spatial location as well as timestamps. And using that, we deduce that the generalization was relatively easy, somewhat natural, but that led to the feature that clocks which are in relative motion seem to tick at different rates. And this is not just the artifact of whatever generalizations we cooked up, but it was experimentally verified in the decays of the particles called mu mesons. Today I am going to look at something different. We are going to discuss something completely different feature, and that has to do with phenomenon of fluctuations and the existence of microscopic structure, something that is not visible to the eyes, nevertheless it exists, and how does it manifest itself is what I am going to describe. So, there are two sort of experiments that I will discuss, or implications of two experiments, and from that I will not go into many derivations or anything of that sort. So, it will be sort of telling a story, but that is enough to give hints as to what is the importance of and how do you discover that there exists a microscopic structure. So, that is roughly the theme of the talk today. So, I am going to talk about, today I will need to refer to some dates, etc. So, I need to refer to my notes. So, two things that I am going to talk about is something called Nyquist result, and second is the Brownian motion. I think you have got some introduction to that already from Professor Balakrishnan, right? So, some part may be already little repetitive, but that is fine because I am not going to go into many details. Okay, so let us begin with one. This is not the historical order in which I am proceeding, but it is easier to present first part because it is shorter and then longer part. So, I am reversing the historical order. Okay, so first thing is in 1926, Johnson discovered that electrical circuits show fluctuating current even when there is no power source. You can see it at the back. Okay. So, this is a bit strange that you are looking at the circuits. There is no power source, no battery, nothing plugged in the sockets, and somehow you seem to find the ammeter needle, or that was the time people would have used those instruments, is somehow moving, fluctuating, and you can try to find out how much the fluctuation and say why there is no current going. I am not putting in the battery, nevertheless there is a fluctuation. Why is it that? So, a good guess was made that this is probably because in the circuit there are conductors and resistances and whatever else. So, they are made up of matter. So, perhaps there are some charges which you know that current is because of movement of charges. So, charges are perhaps moving in some random fashion, and maybe because of that there is a fluctuation and that induces current, and that is what one is seeing. So, it's a guess was good that there may be some fluctuations in the charges which is causing the current. But how do you measure and how do you find out what is the quantitative properties of these. So that was done by Nyquist, and that was in 1928. He gave the quantitative explanation. The paper is very simple and nice actually. The paper came in Physical Review D, 1928. I will just repeat the argument. The argument is very simple, which is why I can present it. He first observes that, so consider idealized circuit in the sense you have got two resistances and they are connected by some conductor. So this is resistance R. You take the resistances to be the same, and there is some connecting wire, whichever way it is. I mean, arrows don't mean anything here, so let me not put the arrows. So just a closed circuit. Okay. And this is the kind of thing which produces this fluctuating current, and one observes that. The question is, so he argues as follows: suppose there are some electrons or charge particles here, I mean charge carriers, which are fluctuating, which induces a current in this. If it induces a current, say going in this direction, doesn't matter which direction it is, then it is going to cause this resistance to heat up. Okay, so let me call this as conductor C1, conductor C2. Okay, the resistance part which is the same, it's just some material which is different. So this will cause some current to flow. This current will induce passing through resistance, will heat up the resistance, and therefore some energy transfer is there. So there is some power transfer in this circuit because this is causing the current to pass through. Okay, let's also note that this entire circuit is kept at the same temperature. So you immerse in some bath and keep it there. So that means this guy and this guy are at the same temperature. Now, but who says that the current fluctuation happens only here? Fluctuation can also happen here. So if so, then this fluctuation will also cause a current to be induced that will pass through this resistance and also produce some current I prime. First one produces I, this one produces I prime, let's say, and then it will also cause the heat to be generated and the power will be transferred from fluctuations to the resistance. But because they are at the same temperature, at the equilibrium, whatever heat is produced here must be same as heat produced here. So this balance will imply, therefore, the two currents which are produced are equal. Okay, very simple argument. But now notice that this argument itself doesn't specify anything at all, except that there is some resistance and a macroscopic property that if through a resistance a current passes, it heats up. Apart from that property, no other details of the resistance, what material it's made up of, what conductor it is, none of those details are important. Okay, so that shows that whatever happens, whatever is doing this phenomenon, these details are irrelevant. They don't matter. Secondly, you can also remove this and say take these wires and put it in a fluid, say water with electrolyte, and that will still form the circuit. Exactly same argument will go through because it doesn't matter what is connecting it. All it matters is that some fluctuations here induce current, that current passes through this, it heats up. Similarly, this way, heating must be the same, therefore the answer must be the same. Okay, as simple as argument as that. But this has the power that it says it doesn't matter with too many details. It doesn't care what the microscopic structure of the resistance is, what value it is, and so on. One has taken it to be equal because the two currents then turn out to be equal. Second property is that, so this is one macroscopic property that if a current passes through resistance, it heats up. Second property is that across the resistance, you are going to develop a voltage difference. So if a current passes through that, there will be some voltage difference. This voltage difference is resistance times the current. Okay, all right. So far so good. So this just shows that I can get rid of many details and the phenomenon will still exist. Okay. Now comes the important change. You replace this by what is called a cavity. So it's something like a metal cylinder you will just put. Okay. Now because the charges are doing something here, it excites the electromagnetic field. So how much electromagnetism you have done? Maybe not. So let me just state certain facts and you accept that. You will study more details of this when you go further classes. So if there are charges moving, then that moving charges will produce electromagnetic field, and that electromagnetic field passing through this kind of what is called waveguide or a transmission line, some device which goes like this, can be just a pipe for example. It will excite electromagnetic field here, and the laws of electrodynamics, Maxwell's equations are such, it will tell you that this will excite electromagnetic field which are in the form of waves which have certain wavelength. The wavelengths can be various. One largest wavelength will be having twice the length of this waveguide. Okay, and there will be multiples of this, just as you have waves which go like that. You can also go something halfway and so on. Sorry, it should also go the same way. I'm putting notes there. So you can have multiples of these frequencies or wavelengths which will be fitting inside. All of those can be excited. How it is excited, etc., don't worry about it. It's just excited somehow. You do some disturbance. I mean, it's a bit like your pipe. You put a hammer on that. It somehow start doing. That's all. Similarly, electromagnetic field is going to be excited. Is going to be doing something. Now, when the electromagnetic field is excited, one has an expression as to how much energy is communicated in that. Okay, so what was our earlier logic? Fluctuation here induces current, which transfers power here through the wire which was there. Wire has been replaced by this new device. Okay, but here we know how much is the energy transfer here. That's a separate calculation as to if an electromagnetic field is excited within a cavity like that, then how much energy is transmitted per second. Okay, I will quote the formula because I will not derive that. And the formula is as follows. So this is fact we have to know. Energy circulating. That is because the wave will be going back and forth. So some wave will travel this way, some wave will travel that way. There will be standing waves formed and whatever it is. So energy circulating in the cavity per second, let's say per unit time, is proportional to or is given by, let me write it and then explain. Delta nu times K is the Boltzmann constant, temp T is the temperature. What is delta nu? Delta nu is, see, there is when this is the fields inside are excited, they are not coming at one frequency. But there is some accuracy is there. So there is some multiple frequencies will be excited. So just 1 minute. So the number of frequencies which are excited in the width, so given frequency and little bit plus minus, that is this number delta nu. Okay. So given the cavity, it has the characteristic properties. There will be certain delta nu will be available called the bandwidth. K is the Boltzmann constant, T is the temperature. Energy circulating in the cavity is then given by this. Yeah.
Sir, could you explain the excitation and the formation of the waves again?
If I hold a charge here and shake my hand, what will happen? A single charge sitting here will produce electrostatic field. If I keep moving it, then it's going to have, my hand is not just moving steadily, it's having acceleration. That is going to radiate some electromagnetic field. That field is what is being, if there is some reason for which electromagnetic field is passing through that, then because this has certain shape and certain boundary conditions are there, only some kind of waves will survive there, remaining will die out. So that is what I mean by saying that if there is any fluctuating current means it's going to change, like my hand moving, accelerating, it's going to induce some electromagnetic field, excited some fashion, but ones which survive here are exactly the ones which will satisfy the specific boundary conditions, namely they must vanish at the end points and so on. That will tell you what kinds of waves exist, what are their frequencies, and depending on the length of this, how much of delta nu you can have is what is decided by the cavity. Okay, all right. So this is the power which is there. We know the power passing through this is heating is I times R square, R times I square, right? So power passing through this we know, but we know that in equilibrium all the powers must be equal. That is the argument we use for the first two cases. Okay, therefore you must have. So now what is the situation? Previously there was a excitation, a fluctuation here which caused current which heated this up, vice versa. Now fluctuation here which causes current which excites this cavity, which transmits the current here and this passes through, and vice versa. So either way you go, you should get same answer, which means the power which is residing here or flowing back and forth must be same as the power which is consumed in the resistances or in the combined circuit. So if I now put a voltmeter here to find out what the voltage across this is, I can find out this is like a battery, there is a circuit, there is the internal resistance of this, because there are two resistances. Resistance is 2 or 2 times R. I know the current, voltage difference divided by resistance is the current. Given the current, the power which is consumed in the resistance is R times I square. I is equal to V by R. So I find out and get a relation. That relation is equated to this one. Okay. So now we get delta nu, not change in frequency, the number of frequencies which are available. It's not one frequency which is there. So frequency which is mean frequency will be something, there will be some plus minus frequency values will be, that is delta nu. I will give the numerical examples I will give in a minute. So let me just write the formula. So this part we know, resistances are telling me, so induced voltage, sorry, next question. Yeah.
Yes, sir. How are the fluctuations? The fluctuations in current. How is that coming in a closed circuit with no connections?
Inside the material, the fluctuations are there.
Yes, sir. How, sir?
That is because of this guy, temperature. Okay. So when we write few more equations, you'll see why I am getting there. But let's just assume at the moment, because that was a guess. Why is this in the first place? Why the fluctuating current is there? Guess was that there must be agitation of some electrons for whatever reason, which is doing that. How it happens, we don't know yet. Okay, we'll come to that. Right now we don't know. We only know this is a fact, it happens. Because of this happens, because of equilibrium, they must be equal. That's all we know. Now given this, the induced voltage is 2R times I, because there are two resistances. So 2R times I is the voltage drop across this, and power dissipation in the heating, that is equal to I square R, and then you will get therefore V square divided by 4R square, V by 2R is I, square of that times R. Okay, this is the current which is power which is dissipated here. This must be equal to the power which is residing in the cavity, and that is equal to delta nu K times T, which therefore tells you, now this I am calling V square, but this is because of fluctuation, so we will call it average. The notation is simply this. R is fixed, the current fluctuates, so therefore current is denoted by average, so voltage difference is denoted by average. So this then tells you that average V square is equal to 4R KT delta nu. So you measure this and try to find out, this is the quantitative relation now proposed. Earlier it was only qualitative, that if you heat up the thing, then the fluctuating current is more, voltage drop will be more, and so on, but he didn't know what is the relation between this. This argument of saying that the powers must be equal and knowing what the power in the waveguide is, tells you the relation must be such and such. Okay, we could have replaced by something else. If you knew how to calculate for electrolyte, we could have used that, we will still get similar result. Okay, so this is the quantitative result that Nyquist obtained, and then this is something that can be measured. Okay, because every quantity of voltage difference can be measured, temperature is known, for the cavity you know what delta nu is, resistances are known, so you can verify that the relation is true or not, explicitly measuring it. Yeah. Sorry? Delta nu is just the small window in the frequency. So for example, I may have the central frequency, that is the length being L, so wavelength will be 2 times L. So frequency will be C divided by 2 times L, that's the mean frequency. Okay, but the length may not be exactly what it is. So there will be little bit of fluctuation, and the frequencies will not be exactly that nu 0, but nu 0 plus little bit and nu 0 minus little bit. So frequency will not be, let me write the numbers, then you will see, just give me 2 minutes. So just to get some numerical thing, and that will also explain what delta nu is, let me quote some numbers. Just 1 second. So let's take the temperature to be about 300 degrees Kelvin, like room temperature. Okay. Or if there is a factor of 2 or something, just fix it. Okay. The exact factor doesn't matter, because what is relevant is proportional to resistance and temperature. Remaining factors are of course important for actually verifying it true, but I am not being so careful here. So let's say the temperature is about 300 degrees. Value of Boltzmann constant is known. So in MKS units is 10 power minus 23 joules. So this will turn out to be approximately 10 power minus 21 joules. Okay, all right. Now resistance is, let's say resistance is about 1 kilo ohm. So about 1000 ohms is the resistance, let's say. You can change these numbers because you may do experiment with different resistances and plot the curve and so on and so forth. I am just giving estimate to see how much V square do you expect. Just for that I am putting some numbers to get a sense of delta nu is of the order of 10 kilohertz. Okay. In that case, V square turns out to be about 10 power minus 14 volt square, or square root of V square is about 10 power minus 7 volts. So that is the amount of voltage drop you are going to see. Okay. Remember, this is fluctuating, so you are not going to say that voltage is always positive on this side and negative on that side. You are going to see sometimes positive here, sometimes negative here, but the difference between these, if you average over or measure it several times, then you will see that average is going to be of the order of 10 power minus 7 volts. So 1/10 of a microvolt. For the temperature, room temperature, resistance of 1 kilo ohm and so on. Now when I say 10 kilohertz is the event, suppose the frequency, actual frequency is maybe 100 kilohertz. Okay. So that means the wavelength is such that the main frequency which is excited is going to be about 100 kilohertz. But it is not exactly equal to 100, but it can be anything between 100 kilohertz plus minus 10 kilohertz. That delta nu is what, that difference is what delta nu is. Okay. Is that clear? Yeah. By equating the power in the heating, which is this part, with the power which is circulating in the cavity. Because power which is going from one to the cavity to the other and reverse is the same. So every ingredient, every element of the circuit must consume same amount of power. There is no accumulation of thing anywhere. We are trying to find out how much is the induced voltage. Yeah. So this relation between these two tells you what the relation between induced voltage is given the frequency range and so on, and the temperature. Is that clear? Okay. You had, does this answer your question what delta nu is? What delta nu represents? Okay, if I have a wavelength, let's say this much, 1 meter wavelength, and I have say it's not 1 meter, but it can be 1 meter plus a centimeter or 1 meter minus a centimeter. So the window which is there is 1 meter plus 1 centimeter minus 1 meter minus 1 centimeter, that is 2 centimeter. That is delta nu. This is for wavelength. I can ask the same question about frequency. Frequency will say that what is frequency? It's 1 over the periodic time, right? So if the period of the oscillation is say 1 second and it changes between 1 second plus little bit and 1 second minus little bit, then the difference between these two is the change in the, or not change, but is the error margin between the periods which are there. That inverse of that will give the error margin of the frequencies. So that is the window. So this delta is not coordinate differences, like this delta has nothing to do with yesterday's deltas. Okay.
What exactly is the
frequency of the electromagnetic waves. Oh, sorry. Was that the question? Did we? Yeah, that was your question? Oh, okay. I'm sorry. Yeah, sorry. See, some things are sort of automatic here, so I don't realize that you are saying it for the first time. So please do ask. I mean, that's fine. That's perfectly okay. So the frequency I'm talking about, the frequency of the electromagnetic waves, not sound waves. Okay. Sorry. Thank you. Thank you for asking this. Is that clear now? That was your question. Okay, sorry, I didn't understand it. Is that clear now for others? You had the similar question? Or maybe it didn't bother, but it doesn't matter. The fact is that electromagnetic field is excited, there are electromagnetic waves, and these waves have a wavelength like any wave has, and frequency. It is the frequency range which is the delta, which is called a bandwidth, okay, for the device. It's called a bandwidth. The frequencies with minimum and maximum frequency within which it varies. Okay. So this is one relation that you see. Now observe that in the relationship that you get here, this fluctuation depends on the temperature. So temperature has something to do with that. Okay. It is also, since it is coming from the current, it has something to do with the motion of the charges. So motion of charges and motion and temperature, they seem to be related in some fashion. So one can say that it's temperature which is causing this agitation in the charges, which does this thing, and then lo and behold, without knowing any other details of specific model of water resistance is, water charges are moving, etc., simply noting the fact that the system is in equilibrium is enough to tell you such a relation. Okay, so that's the beauty of this. Now one may say, okay, so what, fine, this is nice, interesting. Does it have any practical implications? Answer is yes, because now imagine you have a circuit in which you have put various complicated things, maybe your computer circuit board or something, and you are going to pass the currents based on your commands that you give, but they are all going in say millivolts or microvolts, sometimes nanovolts, depending upon the precision that you have. If the thing is not in the right temperature, you are going to get these arbitrary fluctuations coming in. Now sometimes when you say that voltage is here, I call it up, voltage is here, I call it down, or this is binary 1, binary 0. But if the fluctuation takes you here, my 0 might become 1, right? Because the fluctuation is random. I have no control over what this value is. I know the amount of that, but I don't know. So if you want to reduce that, I must either lower the temperature or do something else. So whenever you do precision measurements, okay, in this particular context, electrical measurements, then it is important to be aware that such fluctuations exist on which you have no control. They simply are there, and you must factor them into your calculation or estimation of errors and designing the experiments or instruments. If you don't do that, your answers will be meaningless. This is very dramatic when you talk about gravitational wave detection or any precision experiment that you do. You need to take care of the errors. Source of errors, basic error is this kind of thing. This is just an example. There are a whole lot of things. Okay, yeah. How do I conclude? Simplify the fact that they are related. There is a temperature relation between them. If it's a little hotter, this is going to be larger. But I don't know the mechanism by which it happens. That I don't know. For that, I need to invoke kinetic theory or something, which say that if the body is there, gas is there, it's made up of molecules, blah, 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 blah. So many things. Then only I will get, now I have a microscopic understanding of what the phenomenon is. But macroscopically, that the relationship exists is enough to tell me something is happening underneath. I am trying to emphasize that part. Knowing macroscopic manifestations, you infer there must be something happening underneath. This is one example of that. So let me go to the next example, otherwise I will not finish. I don't want to repeat yesterday. Is that part clear? And the message is clear or not? Technical details are less important. Okay. All right. So second example that I am going to mention is Brownian motion. I am using the word already because you have some exposure to that already. So this was again something, this is historically came earlier than this Nyquist thing. So around 1827, this you might have already heard. Robert Brown observed the zigzag motion of pollen grains under a microscope, blah, blah. You already are aware of it. And the motion is something like this, it will go something like this, some arbitrary paths like that. He correctly guessed that yes, this must be because of some underlying thing which we do not know. Otherwise, why would these pollen grains keep moving like this? They seem to be going in random direction. There is no particular regularity to that. So it must be something invisible, what they call invisible active molecules or whatever, because people didn't know what molecule existence was there. That was under doubt. So maybe that is what is causing this. So that's a natural guess. Something is there driving it. That's all you can say. So that guess was correct. This was also, it never stopped. It was also observed if the temperature is higher, this seems to agitate more. If it is the liquid in which it is suspended is dilute, it seems to agitate more, so on. So these qualitative features were seen experimentally. Okay. Now, kinetic theory was around, ideas of kinetic theory of gases and by extrapolation to fluids, dilute fluids was around, but it was not believed fully. It was doubtful that, well, maybe there, but I don't really know, there is no direct evidence of that, so why should I believe it, etc., etc. So there are many doubts about it. Okay. So they said, all right, one natural test is that here is something which is visible. If these pollen grains are following this, your kinetic theory, then surely I can measure the average velocity of this. I know where they are, I can track them, measure them, find out the average velocity. That average velocity square should correspond to the equipartition theorem as followed from kinetic theory. Okay, that was the natural guess to do. So we should see that this V square should be equal to kT over 3m, mass of the Brownian particle. Okay, that was what was expected, and it failed completely. Okay. When we measure this and try to find out, the answer does not match. So they say, oh, this is an evidence, kinetic theory is all nonsense. This one, oh, that's the equipartition theorem. This is again average velocity. So what does kinetic theory says? Kinetic theory says that there are these little molecules or atom, tiny particles which are free. They are always moving. There is nothing to stop them. They collide with each other. The collision conserves the energy, so it's elastic collisions. So that happens, and their agitation is proportional to what you manifest as temperature. So if you hit the body, that's what it is. Then there is a calculational detail which will say that if you measure how much is the average velocity, then average velocity of all these different molecules is a measure of what the temperature is. That's a consequence of kinetic theory. So I'm using that. This relation is called equipartition theorem. So per degree of freedom, there is half kT is the value that we respect as per the kinetic theory. So thermodynamics will tell you that that should be, statistical mechanics will tell you, kinetic theory in particular, that equipartition theorem says per degree, excited degree, there should be half kT is the average energy is there. So this is free particles, so half mv square, this is 3 dimensions, 3 degrees of freedom, so 3 by 2, half of cancels, 3 is there. Okay. So this is something that one expects. If kinetic theory is correct, this should happen, but this is not what happens. So something is wrong, and that's the time when Einstein comes in. One of his 5 great papers, and he says, aha, but you are not interpreting things correctly. Okay. This is not, this velocity that you measure has nothing to do with this velocity. That sounds a little weird. He said, no, that's not what it is. Actually, the path that you see, this path that you see, which is say one segment of that is this one, this is not the ballistic motion as assumed or postulated in the kinetic theory. It's not a molecule going from here to there, but it's actually made up of several microscopic paths like this, and it's this part that you see. This is not really this, but it has a microstructure like this. Okay, and these are the ones which are caused by perhaps these underlying molecules, which what the kinetic theory is talking about. Okay, now if that is the case, then the average of such paths will mean that I calculate average velocity here, velocity here plus speed here, add up all of them, divide by n such kicks, and then that number should match with this one, the equipartition value, and not the number that I will get this distance divided by time taken by this. Because the particle going from, Brownian particle going from here to here may not go like this, but it may do all kinds of crazy things here and then eventually reach there. Okay. So that being the case, the V square that you calculate average has nothing to do with the V postulated in the kinetic theory. So that is not the measurement one should do and then conclude that the explanation is false of kinetic theory. This was Einstein's observation. In fact, one can know that the number of collisions that it will suffer is of the order of 10 power 14 per second. Now, if there are so many tracks, there is no microscope or something that you can watch it and say, here I am tracking this thing. So I am not going to be able to measure the individual V's and calculate their average. I am not able to do that. Okay. So V square that I observe is this tracks something different. There are consequences of something which is happening underlying, which has its own properties, and all I know is this. Now the question to ask therefore is not whether it is supporting kinetic theory or not, but can I measure I am interested in only finding out what this object is, call it displacement. So it may be going something, so I track it, start the time clock, watch it for some time. After some time I see that the distance is so much, and so on and so forth. I find out what is this d as a function of time. Okay, and if you do that, that is what one should plot, and that is the property to be studied, and not the equipartition theorem and so on. Okay, is this part clear? That was a very non-trivial observation, but that was Einstein. All right. Then Einstein's, yeah. Oh, this d is the distance between these two. It's called displacement. Displacement. No. It has this path. Okay. Initial point is this, and finally it has come here. I just find out this distance. Okay. So that's why I said I start the clock, watch for some time, and see where this particle has gone. I repeat, keep doing so many times and find out what is the average thing. I'm not even talking about tracking this in between. I could, but I don't have to. So study it as a function of time. How much is this displacement as a function of time, and see what the properties are. Okay. Yeah. I will give the answer in a minute. I will write down the answer. I'm not going to derive it because you probably have done it already with random walk and so on. I'm just going to state the answer because I want to draw certain conclusions from that. Okay. Alright. So the relevant quantity to study is really what is this displacement as a function of time. That's what one should study. And then Einstein does it, and he say, alright, he uses probabilistic arguments to say that let me assume that there is a probability distribution to say that particle at x goes to x plus delta in time tau. There is some probability for that, f of tau, f sub tau of delta, right? So something like this quantity. Probability for x going to x plus delta in time tau. So watch a Brownian particle, assume there is a probability distribution, and then you have to make some assumptions about, because the probability, it must be always positive, its integral over delta should be sum up to 1. And there is one more technical assumption is there, which I will not write this. And if you use that, then it deduces that consider now the number density of Brownian particles. Okay, in this fluid, how many Brownian particles are there? At each x, find out around that how many particles are there, and it varies with the function of time. So find out what is this quantity, n t x factor. This is number of Brownian particles in the region small volume around x and at time t. Then he shows that this quantity actually satisfies the diffusion equation Okay, I will just write the solution on that. Okay.
So is n of t comma x, is it the total number of particles?
Number density, number of particles per unit volume around the volume element is centered around the point x, x vector, and these are Brownian particles. Okay. How does it vary? He finds out, first of all, he shows that satisfies the so-called diffusion equation, which is where some technical assumptions are needed. The solution is something like this. Again, the details are not that important. I want to draw attention to certain things which I am writing the formula. E to the minus x vector square divided by 4 dt t to the power minus 3 by 2, where it is a constant. For diffusion constant. This can be measured experimentally. So this is what it deduces by probabilistic arguments, assuming that f of tau exists and then it has certain properties to be done. then you can calculate how much this quantity, and shows that this is the answer. Okay. All right. The important point here is that this number density falls off as t to the power minus 3 by 2. Okay. Since number density is number divided volume, the volume occupied goes as t to the power 3 by 2. Since volume is 3-dimensional, the average distance it will go, displacement d will therefore go as t to the power half, mean distance here. So this is again, this density is average, so mean distance will correspond to that. Now you can have different theoretical models and calculate. I am not going to do that. I only want to focus on the fact that the observation that Brownian particles are following these tracks because of something underlying which is causing many microscopic tracks in such a fashion that the net result of this is to say that the average distance covered by the Brownian particle as a function of time goes as t to the power half. Okay, that is the moral of the story here. All right, there is another feature which is there, which is independent of this now, which has to do with phenomenon of viscosity. Okay, this is something that I don't know whether you do the experiments or not, but if you take a ball bearing and take a, say, water or any oil, you keep wearing it, drop the ball bearing from there, then it will start falling. At some stage it will form uniform velocity and finally reach the ground. Other example is, of course, raindrops, which you would have all calculated. So if you were to fall at from 3 kilometers, how much it will hit you and so on and so forth. So you know that there is a notion of terminal velocity, or called drift velocity. So as it is falling, because it's falling in the atmosphere and the medium, there is a resistance offered by that. That resistive force must match with the force of gravity which is pulling it downward. When that happens, the net force on the falling object is 0, therefore speed remains constant. That is the drift velocity. And there is a Stokes law. Very good. So frictional force is equal to 6 pi eta A times V drift. Right? All of you know that. Very good. A is the size of the object, radius of the spherical object, spherical whatever average radius. This is the ratio, the frictional force at when the force is matching and you get drift velocity. The value of the frictional force is something proportional to drift velocity times that. This is something that you know. Very good. Sorry? V drift velocity. Velocity has reached the constant value. Terminal velocity. Yeah. Terminal velocity. Yeah. Otherwise, it can be anything, right? So drift velocity is same as the terminal velocity. Yeah, that's correct. So now you say that, all right, now I still have these Brownian particles, etc. So now they are not only doing all these things, they are also going to experience, if I try to drag them in some way, put charge and put a magnet, electrostatic field or whatever. If I am going to drag it, it's going to feel resistance and it's going to follow Stokes law. Okay. So there are these two things. So therefore, there is going to be, once it has reached this drift velocity or terminal velocity feature, it is going to be causing a current, rho density times the velocity, current which is because of the drift, and current which is because of this guy, diffusion. This phenomenon is called diffusion phenomenon. When you say that the ink drop dropped in the water will diffuse slowly, the volume that it occupies will follow this inverse of that guy, where number of ink drops remains the same, number of ink particles remain the same, shape changes, it goes all over the place, and that's the density dilution that you get. So that's a diffusion phenomenon. So you have diffusion current and you have the current due to the drift velocity. These two must match in equilibrium. All logic is built to equilibrium. Now getting that, he derives the relation between this d and this eta. Okay. Okay, what is this? I am just giving interpretation of what this is, this behavior. Okay. So this is a solution of what is called a diffusion equation, which I didn't write, which is time derivative of n with respect to t is proportional to double derivative of n with respect to x, etc. I didn't write that. So a solution of that equation. That equation itself was found much earlier. Okay, I think 1860 or something, even earlier maybe. So that was known. So this phenomenon of diffusion, something diffuses slowly, was known. I mean, if you have empty room and put gas or gas, your cooking gas opens, it diffuses, right? Or ink drop, you put ink into water, it diffuses. So phenomena of diffusion was known. It was also known it satisfies the variation of density also, satisfies the diffusion equation. Whose solution is this? Which is what Einstein deduced from the probabilistic reasoning for the Brownian particle, which doesn't talk about diffusion. So it shows that Brownian particle motion behaves as though it's a diffusive motion because it satisfies the same rule. So once that is there, so you have got a current corresponding to that. This is number density multiplied by speed will correspond to current density. So current density due to diffusive behavior and current density due to frictional force, that is the drift velocity one. These two must cancel each other so that there is no accumulation of anything in it. So the fact that these two currents must, their divergence must cancel so that there is conservation of this, gives Einstein the relation, namely D is equal to AT times nu, where nu is equal to inverse of this guy. This is the relation called Einstein relation. Okay. The diffusion constant D which is there, because you have two currents. One is current due to diffusion, one is current due to friction drift velocity. These two are matched, and therefore there is a relation between two. The drift velocity current coming from here is related to eta A, so that's inverse of that is nu, and there is a diffusion which is related to D, and the relation between them is through again a temperature T. Again, because you are getting these to be equal, and when they are equated, this guy should behave as Boltzmann distribution. That brings in the temperature. Yeah.
Sir, you said that diffusion constant is a property of the medium, the liquid which
Yeah.
it is. So then why does it depend upon the radius of the radius of
No. So diffusion constant by itself doesn't depend upon that. This relation is saying that if you have these two processes going on, diffusive process and process due to frictional force, and if they are in equilibrium, they can be in equilibrium only if the D and this satisfy this relation.
so
That is the interpretation. It
so-
is not a priori, it is that. No.
so for different
If there is no equilibrium, there is no relation like this.
so for different objects it will differ
Yeah, I guess so.
based on
Yeah, and
based
that
on-
number will also, eta will also keep changing. No. Yeah. Is that clear? This logic is little involves many different ideas, but the end result is this. End result is rather simple. Now, experimentally, this can be verified and was verified. And equating them so that the divergence is equal to 0, so that there is no net current. I mean, that's how the logic is entered, and that gives this relation. Okay. The calculations are not too difficult, but I mean, I can't do it in 1 hour. I'm already reaching my limits. So, I don't want to repeat yesterday. Yesterday was too far. Okay. So, is this part clear? Okay. Now, so what is the moral of the story here? Moral is this Brownian particles show diffusive behavior. There is also viscosity is there, and these two are related if the equilibrium is reached and the relation is such and such. Now, all of this, it's a bit strange that why phenomena of viscosity has anything to do with diffusion, right? There is one reason why it may be related is that both are caused by some underlying common phenomenon. And the common phenomenon we know is this incessant molecular motion, which is not visible. It's manifesting in one way as a diffusion, it's manifesting as frictional force in different way. They happen to be equal when the equilibrium is reached, and lo and behold, the common thing then just is this avatar here, since it's coming from the same one, they must be related, and that's the relation. Okay, so that's how it comes. Now, this can be made much more explicit or more sort of call it intuitive by saying that instead of saying using these probabilistic arguments about Brownian particle as a probability go this way, etc., why not write a Newtonian type equation for the Brownian particle itself, incorporating the features which are something like frictional force is there, because we know that's what happens, and something which will incorporate this diffusive behavior. And that was the step which was taken by Langevin. Okay. So he proposed the following equation. I will just write the equation and solution. They are in continuous motion, and the motion is random. What random means, we'll come to. We don't know. So all we know is like what was said in kinetic motion, that these guys are always moving. We don't know how, why. They're colliding all the time. They're large in number, and then something happens. And what happens is these two different phenomena which are related. Okay. So to see it somewhat more directly is what the Langevins equation does, and that will bring a new feature, which is what I want to draw your attention to. So Langevin gave this formulation around 1908, about 3 years after Einstein's this thing, and he says the following: this Brownian particle motion is non-uniform, so there must be some force acting. So of course you have this standard equation, m ddt of velocity, mass times acceleration. This must be some force. There must be some force because it's not uniform, and that some force, there must be two components to that, because we know that these things are resisted. So if you were to drag it somehow, there is going to be a drag force. Resistance is there, and that we know is proportional to velocity, because that's how we got the drift velocity. So we'll just put it as minus m times tau times velocity v. I will write it and then explain. And then there is one more piece which we do not know. If there is some underlying fellow doing something mischief, it is causing some force which may be varying very rapidly. So there is some random force which I will just call f of t. I don't know what this is. Okay. What is this guy? This just says that this is a coefficient of this. I am going to write as, just because I am going to cancel the mass eventually. So I will just put mass times something. Dimensionally this is dv dt, this is v. So this has dimensions of time. So I just call it tau. Okay. So tau is a constant characteristic of whatever is happening, the material in which the Brownian particle is moving. This is just the Newton's law applied, but new ingredient is that there is this f which is random, which I do not know. That's a new ingredient. Okay. And what does that mean? It means that f of t, this can be function of t, right? If I average it, it is equal to, let me write and explain, 0. So what I do, if I want to simulate this thing, I will start with some initial condition and then put a step to increment it step by step, and at every point of time I will flip a coin and put a force, random force. I can first do it for 1 dimension, so it's easier, otherwise 3 dimensions. So I will put this and then run it. So every time take one time step, one random force, second time step, second random force. I run it for say 100 time steps, and I get a solution v as a function of t for a particular flipping of coin and this f which is there. I can now repeat the experiment again and again. So I generate several such runs and average over that. So these several runs will constitute an ensemble of trajectories as evolved as solutions of this for arbitrarily made choice of f. Okay, this part is clear. If I know what f of t is, I get a solution, either analytically or numerically. But f of t is variable because it's random. So I will run several such solutions and then average over this. To say the average of this ensemble average, literally velocity v1, v2, v3 divided by a number of runs, that will be the average velocity. So I will get this average I will denote as ensemble. These f's are such a fashion that we know that the agitation can be in any direction. So average of this force is equal to 0. So under different runs I do, the f's that I am going to choose, they will average to 0. That is the assumption. Okay, this is an assumption which is there. Now you do this calculation. Calculation is easy to do. I am not going to do the calculation. I am just going to state the results. So this differential equation is not that difficult to solve for this particular case, and you can get some answer. Okay, so let me draw some statements about here. So after getting the solution, I can find out the p as a function of time and then average it. Okay, then you can see that average of v of t the average term coming from force is equal to 0. Just take this solution from me. I mean, I'm not going to explain it. You have done differential equations? Probably not. You might be doing it. This is a simple differential equation that you can solve. This inhomogeneous term, this is first order equation in V. This p times y dy dx is equal to py plus q, integrate it, then you will get a term which is coming from here, integral, and a term which is integral of f. Average of f is 0, so when you take average, that term vanishes. So yes, you only get this one. Okay, that force cannot be arbitrary. There will be relations to that. So that's the beauty of it. Okay, so you'll get this solution, and this solution then implies that average of Vt is something like V0 average. So I can average over the initial conditions. I may either achieve the same initial condition and run the things, or keep varying the initial conditions, up to me, times e to the minus t by tau. And because of this coefficient tau which is sitting is called a relaxation time. It exponentially relaxes. So if you started with velocity, average velocity, as the time changes, it starts decreasing, eventually goes to 0 over a period of half the time. So half thing will be, so tau is called a relaxation time. Okay. Here tau was introduced only as a dimensional quantity on dimensional grounds. Its interpretation is that it's a relaxation time. Okay. Tau is here just some parameter which is there, some constant of the system. I do not know what value it is. I don't know its value. So tau is just a constant which is there. Typically one calls this object to be gamma, which is called a friction coefficient. So it's a friction coefficient, but I'm skipping those steps and writing it because I'm going to divide by m and write as a remaining object. Dimensional ground has to be a time dimension. So I'm just calling it tau. And calling it tau, interpretation is that the solution will be doing this. So it says that a parameter tau tells you how the system relaxes. If I have average velocity in this run, if I keep running it for longer time, how is it going to be as a function of time? It is going to fall off exponentially with a parameter characteristic tau. Tau is the one which is sitting in the equation. That equation determines what it does. Okay. Yes. Cheap way of doing the calculation is to say write the equation and then put the brackets. That's average. But that will say that you are averaging the dv dt, ddt of v, average of the acceleration. Correct way to do is solve the equation first for a given run and then do the average, because strictly speaking, average of dv dt is not same as ddt of the average. In general, it is not true. That's correct. I sort of just made a sly remark. The correct way to do is solve this equation, then you get a solution for a given run. Now average it, then you will get this solution. Yeah. I mean, the solution will be that. So I have not written that, the intermediate steps I have not written, but it is correct. What you said is completely correct. While taking averages, one has to be careful that whether you take average of the quantity and take derivative or vice versa, that are not in general equal. Sometimes they are equal, but not always. Okay, so what are the features that you see in this? Now it turns out, analyzing of this equation, so I will just summarize that, and that's where I will wrap up the talk. So there are following features that it has. It may happen that the average velocity that you find out by doing this experiment, running it so many times with different f's and so on and so forth. So if average v square has reached the equilibrium value, that is average v square is equal to kt by 3m. If it somehow happen to reach this value, then it will remain there. It will not change after that. Okay? Because now this is time independent, so it reaches the asymptotic value, right? Then it remains there. Secondly, under this condition, now I can take once I have the full solution, which I am not writing, then for short time, little t compared, very small compared to this tau, you will get the relation. So under this condition, for t much less than tau, you will see the following: average of r square is the distance, displacement in 3 dimensions, r vector square. Average of this goes as average of v square times t. So that is like r is equal to v times t. that's behaving, this object behaves as though it's a ordinary Newtonian particle. So that's the ballistic motion that you will get, but this is for t much smaller than tau. Okay, I'm just stating what the solution properties of solutions are. I'm not deriving the solution. Okay, for t much greater than tau, however, same r square quantity goes as t, which means average r goes as square root of t. So this shows the diffusive behavior. So this dynamics, proposed dynamics with the feature which is coming here, and this f which is random in a particular way. I only specified one property, I will quote the second property in 5 minutes, has the feature that is solution. When averaged over all of this, averaging is necessary because the f is random. So I must average. Given that, these are the properties that you see. It can either reach this. If it has reached it, then the r square behavior as a function of time for small t behaves as though it's an ordinary Newtonian motion, but for large t it behaves like this. So it has both ballistic motion that we will expect in kinetic theory, as well as diffusive motion as we expect from Brownian particles. Okay. Secondly, yeah, r is it is particle in 3 dimensions. It has a vector r, its magnitude. Because the solution is differential equation for v is dr dt, dx vector dt. So calculate r form. So you have to integrate. I am not writing the solution, but yes, that's correct. Now, if second case, so first case is where it has reached the equilibrium value. Second case, it does not reach the equilibrium value. Then what happens? If v square has not reached equilibrium, then it can reach equilibrium only if the f satisfy one more property, namely integral ds minus infinity to infinity f of t plus s this must be equal to 6 times k times t divided by tau divided by m. Okay. So either it has reached the equilibrium, then this is what happens. It shows the behavior of ballistic motion as well as motion diffusive. But if it has not reached it, there are two cases, because when you solve the differential equation, you will get two cases to solve. If it has not reached, then it can reach the equilibrium. You will get the solution. You will see that terms of Anish, etc. Provided, because now you are going to calculate r square, so you will get f times f. So this is what you will average. Sorry, excuse me. Crucial. F is that same force. S is a parameter. S is integration variable. So it's technically called autocorrelation function. This average is called autocorrelation function between T1 and T2. This happens to be the equilibrium depend only on the difference of this, etc., etc., etc. Okay. So you are given this f. You are taking f from various samples. You simply calculate f of T1 and then calculate this integral. This operationally is well defined. Even if you don't know how it comes and so on, operation is completely well defined. Provided that if you choose satisfies this relation, then the v square will reach equilibrium value. Otherwise, it won't. If it satisfies this, so this can reach the equilibrium value only if this is true. Okay. But now observe. Yeah, just 1 second. One of you asked question about what do I take for f. You cannot take a completely arbitrary, because its magnitude must be related with temperature and this parameter tau, sorry, and the mass of the object. It is not arbitrary. If it is not matching it, you will not reach equilibrium. Okay. Remember, our previous examples, we always had property of equilibrium and the results were true only in equilibrium. So this is showing this dynamics, which is Langevin dynamics, as an illustration, is showing that if you introduce a random force and a frictional force, So what is called dissipation and fluctuation. Then you can exhibit the Brownian phenomenon completely. You will get ballistic motion for small time, you will get diffusive motion for large time, and you can reach equilibrium provided this condition holds. So this relation is called fluctuation dissipation theorem. It's one of the properties of this. The fluctuations part, which are the fluctuating part of the force, dissipation because it's the coefficient of the second term, friction force, the velocity proportionality 1 over tau. They must be related, and the relationship involves temperature. Okay, so again it's related to underlying agitation, which is caused by temperature. So again you see that even if I didn't know that underlying molecules exist, if I simply made these assumptions that they are doing whatever is doing, there is some random force, then I can reproduce the result that equilibrium is achieved, provided this is true. Then you can ask further questions microscopically, can I really produce this, etc., etc., etc. So one is going step by step. There is an observed phenomenon. I can make some guess about it. Having made the guess, try to verify it, what relations I get. Those are fine, then I continue, and so on and so forth. So first part only said that there is the probabilistic reasoning from Einstein and the observed phenomenon of Stokes equation. These two together in equilibrium again will get a relation, Einstein relation, which is verified. I can reproduce the same thing from Langevin dynamics, focusing on dynamics of an individual Brownian particle. No probability here, but probability is pushed into the randomness of F. Okay, so now let me just draw moral of the story, so to say, and then I will stop. I calculate F, I calculate T. So how do I generate different F? Say one dimension, I toss a coin. If the coin becomes head, I put a number, which type. I get a certain sequence. Typically one will use pseudo random numbers and generate a sequence. Based on that, I will get these values of F. I have one run of 1000, repeat the calculation, come tomorrow, repeat another 1000, third sample, and so on. Calculate these numbers. I know these numbers. Take the average over all these 1000 runs for a given S. See, I am generating 1000 runs, I mean the 1000 steps, right? So here is one time, this is T, T plus S, T plus S prime. I calculate product of these two, product of these two, product of these two, product of these two. That is summation of this integration. This is mathematical, minus infinity plus, you take large numbers. Okay. Okay. So this is how I calculate it. I mean, if I don't want the integration, I could write it as f of t prime is proportional to delta of t minus t prime, where delta is the Dirac delta function. If you don't know that, then to avoid that, I just wrote this. Yeah, it is the autocorrelation function because it's f square, it's not f. Yeah. But not f at the same point, not at the same time, at different times. Yes, that's correct. Okay. Okay, so let me quickly draw the sort of moral of the story. So, if the macro constituents exist but are non-trackable, okay, one is forced to employ probabilistic method because I don't know what to do, so I introduce probability method. That's all I can do, right? Moment I introduce probability, then of course I have notions of averages, standard deviation, correlation functions, all the mathematical machinery comes available. It's available to me. But these are something, I mean, in the first place I introduce probability because I don't know how to track it. And that's my problem, right? That's not problem of the system. System is doing whatever it is doing. It's my problem, I don't understand how to do it. So I introduce some mathematical machinery of probability, then I get all these fluctuations and blah, blah, blah. What does the system care about it? Should the system care about what I do? No, system is doing what it is doing. Nevertheless, I have captured some features of the system because those fluctuations which I calculate mathematically capture some property of system which manifests itself either as fluctuating current or as Brownian motion. Okay, so my probabilistic methods that I employed, simply because I don't know how to do it, track it individually, because numbers involved are far too large, 10 power 23. Those same 10 power 23 is ensuring that whatever I did mathematically, if I have done it correctly, then it will manifest as features of either fluctuating current, which are there, which have no origin, or these random forces enriching equilibrium. So, observation of this random behavior, random forces, is a signature of underlying microscopic structure. Even if I didn't know it beforehand, I can postulate. Only method of calculation is probabilistic methods. I'll find out what the consequences are. The consequences are experimentally seen. So there is a validity, a reality to this mathematically invented model, which actually is real. So that's the message I wanted to get across. Practical applications, as I mentioned, that they're extremely important to track the errors in your measurement. Otherwise, you can go completely off. You cannot make very precision instruments. You have to pay attention to the statistical fluctuations. Okay, and theoretical tool, because this is one way to discover that underlying microscopic structure exists. I talked about thermal fluctuations. There's something called quantum mechanical fluctuations, which you will study when you study quantum mechanics, which is inherently there for all systems. You can ask the question, can I now say that yesterday I talked about maps and metric and so on, that goes into the field of gravity. If the gravity has quantum mechanical structure, microscopic structure, can it be made visible by methods of this kind? Answer is not known. But nevertheless, this is a feature which is a handle on saying how the microscopic structure manifests itself in the form of what is called this guy, which is also called noise. So existence of noise in various features or statistical random force is an indication of underlying microscopic structure. For yesterday's thing, if you want to know more about it, that was actually part of a talk I gave for global positioning system and how relativity plays a role in that. So that talk is available on my personal homepage. It's www.imsc.res.in. This has different parts. One link is outreach. In that there are several different talks. One of them is related to global positioning system, and that has yesterday's details that I gave, but there is a written version of that, notes as opposed to slides. So you can see more about it, how it actually plays a role in GPS, which I yesterday didn't talk about. Yeah.